the vacuum of quantum field theory, in some sense, it is full of virtual particles. But as a state, it doesn't change with time. It's stationary. Nothing moves. So this image of everything moving fast is, in a sense, is completely wrong, because it's a stationary state. It's a solution of the Schrödinger equation where nothing changes. In elementary quantum mechanics, we say that a harmonic oscillator has a ground state, and this ground state is a Gaussian mathematically. In the ground state, the oscillator is in the minimal of the energy, but with some probability distribution. Okay, and the state never changes. It's just that. If you let it untouched, it stays that. Now, if you look where the particle is, if you try to pinpoint the particle, which is a vacuum state, you don't find it zero. There is a probability you find here, you find it there, because that's a spread, the quantum spread of the state. So it's true that if you look, you find it somewhere. Then you look again, you find it somewhere else. Then you look again, you find it somewhere else. Even if you try not to disturb too much, which is hard, you have this spread, okay? But this doesn't mean that there's a jumping particle there. There's a state which doesn't move. The source of the confusion is that we're not talking about particles, okay? We're talking about quantum objects which are not particles. So a quantum space-time is not a discrete space-time.
Right.
It's a quantum space-time. To say that a quantum space-time is a discrete space-time is the same misunderstanding as saying that a quantum particle is a particle that dances there is here and there.
When people talk about quantum fields, they often, to the lay public, give this idea of a temperature field is usually the first analogy. And then they give this idea that it's something akin to an ocean and then there's ripples. But technically speaking, in quantum field theory, it's not a field in the same way that we think of a temperature field. It's an operator-valued distribution.
Precisely.
So they're operators. Is there something else that's going on with the discretization of space in loop quantum gravity that is akin to, well, it's actually operator-valued discretization or something like that?
Yeah, to say that something, it's an operator, it's some variable, it's given by an operator, is precisely to say this variable is a quantum variable, right? This is a mathematical translation of the same thing. And to be a quantum variable, it means that the system doesn't, there is a sense in which the system doesn't have a specific value of that variable, but has, you could talk about a probability distribution of that variable. Well, there's a quantum probability distribution. It doesn't mean that it can be either here or there. It means when it interacts, you can find it here and there. So that's what we call quantum superposition. I mean, when we say a particle is in a quantum superposition, can be here or there, it means if you look, you find it here or you find it there. But you shouldn't think that it's here and there, because the two can interfere. So if you think that it's here or there, you make a mistake about your prediction of the future. So in a sense, it's here and there at the same time. Or more precisely, you can only say that if you look, if you interact with the thing, you find it here and there. But if you want to see what's going to happen later, you have to still consider both possibilities. So that's a quantum superposition. Good. So now if you have a field, like the electric field, or the magnetic field, or the electromagnetic field, quantum field have to be thought as a superposition of different field configurations. So sort of wave function or cloud in the space of possible fields, in the space of possible configurations of the field. So the electric field is neither here like that, nor like that, nor that like that, but it's a little bit of those, and the quantum state gives a probability to each one of those. When you go to quantum gravity, gravity, that's what we learned from Einstein, is a geometry of space. There's a very visual possibility that gravity is just space bending. Good. Beautiful. So in quantum gravity, the geometry of space is not determinate. It's a superposition of different geometries. So here around us, space is roughly flat. Minkowski space is a flat space. But if we keep into account quantum gravity, in the small, it's a quantum superposition of all possible fluctuations. And in this quantum superposition, light can still travel at the speed of light. But if you go into small and bingo, you want to solve what is the geometry here, you find a geometry which is neither this nor that. You find the geometry which have limitations in length. So there's no structure smaller than a certain length.
Yes. Now, when someone's in high school and they learn about gravity, they learn it's a force, and then some clever undergraduate says, actually, it's the curvature of space-time, and then some clever graduate student says, actually, it can be torsion, and then some PhD may say, well, it could be non-metricity or torsion or any combination of that and curvature. Does loop quantum gravity make a definitive statement as to whether gravity is curvature, torsion, non-metricity, or some combination of them?
Great question, Curt. Let me answer in steps. First step, you go to high school and they tell you that gravity is a force. Okay, the sun and the moon, the sun and the earth pull one another with a force which act at a distance. Be careful. Is that false? Or is that right? I believe that's right. That's not false. It's just approximate. It's an approximate description of reality. Okay? If I say, I look there and I see a forest, and you come to me and you say, no, Carlo, you're wrong. It's not a forest. It's a lot of trees with leaves and so on and so forth. I say, okay, I mean, you have a better description, but it's still a forest. Okay?
Yeah.
So once you learn general relativity, you learn that there's a better description. Why better? Because the other description doesn't capture some phenomenon, it's approximate. Okay? So there's a better description in terms of curvature, but in the common situation in which you are, you can still talk about force. It's not wrong to talk about force. It's just proper names for something that happened when you don't look too in detail. That's the first point. So, could we say that Newton's theory is an approximation and general relativity is a true story? I know, of course, because we know there is quantum gravity. So, Newton's theory is some approximation. Einstein gravity, it's a much better description of reality. Quantum gravity is going to be a better description of reality. Is that going to be the last ultimate description of reality? No, come on. Your program is titled Theory of Everything, which is great, but I don't believe we are any close to any theory of everything. Plenty of things we don't know. We don't know what is dark matter. We don't know what is...
it better be, otherwise I'm out of a job shortly.
Exactly. So I believe that your show can go on for a long time before we could ever think about the theory of everything. If we get there, we'll talk about, but we're not there by very far. So every theory, it's a way of describing the world at some level of precision. Okay, it's not one right, one wrong. Okay. Having clarified all that, which I think is important because it's not often said, and because we used to say, it's wrong that space-time is flat. It's not wrong. It's true. It's just not very precise. Around here, space-time is flat. Okay, to all degree I can measure it, is flat. So I'm saying something very right. And if you say, well, but if you measure it even better, it wouldn't be flat. True. To the extent I can measure, it is flat. So I'm saying something right. There is a force pulling down. If I let my hand fall, by force pull down, it's true. Can you say it's false? No, it's true. Okay. So having clarified that, I come back to your question.
Okay.
in general relativity, in the context of general relativity, space-time, gravity is due to curvature. No torsion, no metricity, nothing like that. There are attempts to rewrite general relativity, in fact, is possible, or extensions of general relativity with some more geometrical, different geometrical, more rich or different geometrical. Nothing, as far as I know, that I've given a lot of, that has had a lot of success that allows us to understand better. If you go to loop quantum gravity, gravity is not just curvature. It's certainly not no metricity. It's quantum curvature. So gravity is a geometry which is curved, so it's curvature. But in addition, it can be, as I was saying before, in a superposition of different curvatures. So you don't really change the geometrical language that you use it, but you allow it to be quantum, namely you allow reality to be in a quantum superposition of different geometries. So if loop quantum gravity is correct, the best way of thinking about gravity is that, look, if quantum mechanics is correct, the best way of thinking about a particle is still a particle, but it can be spread. It can be in a superposition of here and there. And that's the wave function. So if loop quantum gravity is correct, you can still think a gravity geometry, but this geometry is spread. So you have a quantum superposition of geometry, the wave functions of the geometries.
Have any people gotten so far as to do interpretations of loop quantum gravity in the same way there are interpretations of quantum mechanics? So some may say that the wave function is some pilot, and then the particle is just riding atop that pilot. Are there any loop quantum gravitists that would say, well, the curvature is somehow riding atop some pilot curvature?
Yes, there are. In fact, there are exactly papers that do what you just said. The quantum gravity is still a quantum theory. So all the mysterious aspects of quantum theory are inherited by loop quantum gravity. So if you want to interpret the quantum theory, make sense to it, which I think is not a bad idea to go into this exercise, there are various ways of interpreting quantum theory. One is the one you just mentioned, the other is many-world, the other is relational quantum mechanics, which I've worked a lot.
Right.
And each one of these can be applied to loop quantum gravity. So if you want, you can be a loop quantum gravity many-world guy, a loop quantum gravity relational quantum mechanics. It seems to me that the relational way comes more naturally. In November next month, I'm going to a philosophy department to give a series of lectures in which that will be one of the main topics. Princeton, I'm invited 1 month in Princeton to give a series of lectures, and I'm gonna talk about how to interpret, how to make sense of quantum mechanics, keeping in mind that quantum mechanics should include also quantum gravity. So the interpretation of problems which are open in quantum gravity that reflect the interpretation of problems which are open in quantum mechanics.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist.